in this
Good
series,
evening, sir.
theory of relativity part in your mechanics course. So,
Good evening, sir.
Yeah, good evening. So, till the last lecture, what did we learn? As we have been discussing informally right before we formally started the class, is that the Galilean relativity was quite acceptable because Newton's law were solid, they were on a rigid footing, and so they were supported by experiments. So there is no reason to bring in any disbelief, and therefore, since the Galilean relativity nicely incorporated all the ideas of Newton's, there is no reason to sort of cast any suspicion onto it. But then came the electrodynamics, the Maxwell's 4 laws of electrodynamics, and then the key aspect in the Maxwell's 4 laws of electrodynamics, which by the way were also proved correct by experiments, is that the constancy of velocity of light. So velocity of light is something which is a universal constant. That was the key piece in formulating the 4 laws of electrodynamics. Now, of course, people wondered how can that happen? Because all waves till then known to them was require a medium to propagate. And then depending on the property of the medium, the velocity changes. Okay. But here we are talking about something else. Okay. And so also, again, taking the cue from the 7th tutorial, last problem is that the wave equation is not invariant under Galilean transformation. Okay. So there is a lot to be desired. And in the previous lecture, we ended up showing one small calculation where people considered that there is this omnipresent ether. Our entire universe is floating in ether. So in that ether frame, the Earth is moving. So if we simply do an experiment, this should actually manifest. But we found out that the delay time, this delta t, that we figured out from from the motion of the light from one point to another, this delta t is amazingly small, 10 to the power minus 17 second, which is immeasurable, and it really tells you that there is absolutely no difference, there is no delay in time. So that sort of cast a suspicion on the ether theory. However, in 1881, 2 scientists, Michelson and Morley, they carried out an experiment. The motivation behind carrying out that experiment was to prove that this ether indeed exists, and to sort of get around or work around this proposition of Maxwell that velocity of light doesn't require a medium and it's basically a universal constant. So now I'm going to share my slides to start the discussion, show you what Maxwell and Michelson and Morley had done. So it's very famous Michelson-Morley interferometer experiment, and I'm first going to share my slides with you. Can you see the slides?
Yes, sir.
Yes, sir. Yes, sir.
All right. All right. You know what is an interferometer? It's an apparatus which takes into account 2 light beams with a phase difference which will interfere. Okay, and you know this concept of constructive and destructive interference, right? So constructive interference is where both the waves participating in the interference, they actually are in phase, and destructive interference is, and so the intensity of the resultant wave is higher than, basically additive of these 2 participating waves. Whereas in case of destructive interference, it is the other way. That is, the 2 participating waves, they are out of phase, and as a result, the intensity of the resultant wave is 0. Right? I guess you know this. Okay. So Michelson's interferometer, it was fixed on Earth. And let us first start with the basic premise, the imagination, is that the Earth moves at an orbital speed of 30 km per second along its near circular trajectory about the Sun S, reversing its direction every 6 months. Now, we consider this ether frame, whatever that is to be fixed with respect to the Sun. Okay, so this entire Earth and the interferometer, whosoever is on the Earth, is moving with a velocity v with respect to ether frame. Okay, that is what. And Michelson Morley experiment was done to prove the existence of this ether. Okay, now this is the setup of the Michelson Morley interferometer. What is it? You have a light source, you have a light beam, okay, emanating from the light source. There are 3 mirrors. This mirror over here is a slanted mirror in 45-degree angle with respect to the perpendicular. Okay, and then there are 2 mirrors. This mirror is a movable mirror, okay, in the perpendicular direction, and a fixed mirror in the horizontal direction. Okay, M1 and M2. So what is happening is that the light beam from this source goes, hits the mirror, a part of it gets transmitted, a part of it gets reflected. So the part that is being transmitted, that goes to the fixed mirror M1, from there it gets reflected, comes back again to this mirror, again gets reflected, and the resultant wave is being observed through a telescope. Now, this is the transmitted part. The other part is reflected from this mirror, goes to M2, gets reflected again, comes back, and again it gets transmitted through this mirror and joins the other one at the eyepiece of the telescope. Okay. So these are the 2 beams. The beam splits, and this is how this thing occurs. So these 2 final beams, they interfere. Okay. So they recombine, and then you get a field of view. We get a pattern, which is known as the fringe pattern. Okay, illuminated field of view. I mean, if it is a constructive one, then you should have all light. You should see a complete illumination, a brightness in the eyepiece of your telescope. Now, it may so happen that either of the beams suffers a delay in reaching this eyepiece. So what do I mean is that is the concept of my destructive interference. So I'm just going to show you that.
Excuse me, sir.
So
which 2 rays are interfering?
These 2, the final ones.
Which are reaching the eyepiece?
The ones that are going to the eyepiece. Because in the eyepiece, you are seeing the interference pattern. Okay?
Okay, sir.
Okay. All right. Now let's go to this. All right. So over here, you see, here I have drawn field intensity versus time. So here are the 2 waves, waves 1 and 2. Do you see that these 2 waves are completely in phase? That is, their peak is at the same value of t. That is, it's happening at the same time. And then their this bottom, or the and it basically it's a sinusoidal wave. So they go to 0 also at the same time. So the cycles are together, and as a result, the interference pattern, the resultant field intensity that you will see is something like this. Of course, it's a sketch, but what it means is that the resultant intensity is additive of these 2. Whereas if either of the beams suffers a delay, for example, that you see with respect to 1, 2 is delayed by a half cycle of oscillation, okay, or vice versa. Because when there is the peak of, this one, they are really out of phase, okay. When this is negative, this is positive. And over here also. So now, when you find out the resultant intensity, what will that be? That will be like this, 0 everywhere. Okay. So you get a full illumination for this part, whereas you get nothing here. So what do you expect? What would be the pattern like? The pattern should be basically alternate dark and bright fringes. Why? Because generally one of the mirrors that I have fixed over here is slightly tilted, and slightly tilted, let's say this movable mirror, I move it slightly tilted. As a result, what will happen? There will be a path difference between these two. So this, if I consider these two are the arms, this length and this length, they may not be identical. Although in the figure it looks like they are identical. So the light has to travel exactly equal amount of distance in either cases. But if I tilt it a little bit, there would be a path difference. The path that the light traverses in going from here to here and here to here is not same as the path that is being traversed from here to here and here to here. Okay, so this path difference will introduce a time delay across the returning wavefronts. So these two waves will go in and out of phase across the field of view, and as a result, the pattern that you will find is alternate dark and bright fringes like this. Okay. So the source of the phase difference of these two beams is definitely, as I said, different path lengths traveled if I make the arm lengths slightly different. But on top of that, there is another possibility that there can be different speeds of travel with respect to instrument because of the ether wind. Remember, the instrument is floating in the ether wind. So it is like, this aeroplane problem that we did in the tutorial, that depending upon the tailwind, the direction of the tailwind, the direction of the velocities of light can be different in different directions. That was the proposition. Okay. So as a result of that, there would be a time delay as well between the wavefronts reaching at a point, and as a result, you may get constructive interference, alternative constructive, and destructive interference. So there will be dark patches, there will be bright patches.
So is it
So this is the
Newton's ring experiment?
Huh?
Is it same as Newton's ring experiment?
In the Newton's ring also you get this kind of thing. This is for any interference experiment. This is the interference pattern, typical interference pattern. Okay. All right. So now let us see what is the consequence, or what we set out to find out, whether we can find it out. So let's do a little calculation. Let's consider this mirror. Okay, so time taken by the light pulse in this branch for a round trip is how much? This very simple thing. I guess I do not have to sort of elaborate why this equation. All right. Now let us consider the other one. It's very interesting. For the other branch, look at the figure carefully and the equation. What have I done? What does it mean? It means the simple thing that if the time taken for the light beam, incoming light beam, to get reflected from this slanted mirror and travel to this mirror and come back again at this mirror is T2, then CT2 is the total length that the light travels within this time. Now, over here, although here it is like perpendicular, but actually here in this figure, this is slanted. Why so? Because this calculation of this time T2 is being done in the frame of the ether. That is, I am standing at the sun where the ether frame is located, and I am observing the phenomena at Earth. So what would I see? I would see that during the time T2 by 2, let's say, that is here, this one heats, it takes some time to go there, exactly half of the total time, T2 by 2. It should have been like this, whereas it's going like this, because during that time, this mirror has moved to this place. Okay. And then when it comes down, it does not find it to be here, this M mirror. Instead, this M mirror has moved all the way to this position. So there would be this slanted ray coming to this. So now this calculation is very simple. If this arm length is in the perpendicular direction, if it is L2, so you can see this equation can be understood. And from there, we can calculate that T2 is equal to this form. All right. Now, remember, why didn't it happen in the case of first one? Because here, the time that we have calculated is in the frame of the apparatus. The time was not finished. The time was not calculated from the frame of ether in this case.
Then, sir, the other mirror M2 is in ether frame.
Everything is in ether frame. Earth is in ether frame. Entire apparatus is in ether frame. No. M2 is not in ether frame. See, ether frame is ether frame. Apparatus frame is apparatus frame. In here, the calculation is done from the point of view, or the measurement of time is done from the point of view of an observer standing in the ether frame. Okay.
Okay, sir.
Right? Whereas in this case, the time measurement is done by an observer who is sitting in the apparatus frame. That is standing on.
Sir, it seems like the
He is the velocity of Earth. So an observer standing on Earth is part of the Earth frame.
Sir, does that mean that the mirror M2 also moved?
Yes. That's what. No.
Yes, sir. Now I got it, sir.
When this light goes, this light does not find the M2 over here. It finds it here. That's why it has to travel like this.
Yes, sir. Now I got it. Thank you.
Right. Okay. So here is this critical thing that you may question, that why did you calculate T1 in the apparatus frame and T2 in the ether frame, whatever that is. It's because Galilean relativity tells me that time has no significance. Time is identical in any of the inertial frames. So I can do the calculations anywhere. Doesn't matter. If I had done this calculation in the ether frame, in the apparatus frame, it should have given me the identical result. Okay. All right. See, it's philosophical. I mean, do not think mathematically. Get the idea, the physical conception that is being used here, a very clever way, using the Galilean relativity. Because when this experiment...
Sir, how do we calculate T2 here?
From this equation. The equation here.
Excuse me, sir, I'm not able to see the slides, sir.
Oh, then check your connections.
Yes, sir, I transferred back again to my laptop, so that's why I'm not able to see the slides.
This I cannot do anything, because if majority of the people are being able to see, it's not a problem with my connection. So I'm sorry, I cannot help you with that.
So I'm rejoining.
Okay. So basically that's what it
T2 equals, sir,
is.
sir, T2
Moving
equals
on.
to 2L2 होना चाहिए ना?
What T2?
What was I saying all along? That I am measuring this T2 from the frame of reference of R. Okay. Right.
Yes.
So from the frame of reference of ether, what does the people see? Anything on Earth, anything, including this, parts of the apparatus, they are all moving in the velocity v. So the observer starts to observe things right when the light hits this mirror M. Okay. Now, the mirror has to see, the phenomenon is like the light has to get reflected from M to come back to M again. All right. Now, what you are saying is that the M2 is still in the perpendicular direction. But according to the observer in the ether frame, everything is moving with velocity v. So after the time T2 by 2, where does the light finds the mirror? It does not find the mirror over here. It finds the mirror over here. Do you get my point?
Okay. Yes, sir.
Okay.
Got it.
And when it comes back, he was expecting that it will go simply down in the perpendicular direction and find the mirror M. But the mirror M by that time has moved again to this position. So it has to bend itself and come back to this point in order to get transmitted.
Yes,
Okay?
got it. Yes.
Yeah.
So M2
So-
is not moving, right? So
Huh? What?
the mirror M2 is not moving, right?
Everybody is moving. Again, please listen carefully. Okay, consider this. You are standing on a platform. You think you are on rest. Inside a train, there are two seats. Two persons are sitting, facing each other. To you, aren't all of them moving? Yes or no?
Yes, sir. Yes, sir.
So it depends on from which frame you are observing. So mark my words very carefully. I am in here, I am doing the calculation or the observation, the measurement from the ether frame, which is not fixed to the earth. Earth and everything on earth is moving with respect to ether with a velocity v. Okay. So therefore, M is moving, M2 is moving according to me. I mean, according to me standing on ether, everything is moving with the velocity v. And this is a consequence of that.
Sir, here then we can only say this if L2 is a significantly large distance, right, sir? For small distances, this won't satisfy the condition that you're
What
saying.
is large, what is small? How large is large, how small is small? Those have no meaning. Okay. Wait, I mean, guys, please wait. Let me go little far and then ask questions, then jump into conclusions. It has got nothing to do with this length. These lengths are typical finite length that we care about. Okay. So the time difference for these two light beams from M1 and from M2 to come to my eyepiece or come to this point M before being transmitted is T2 minus T1, which we can calculate. Now, what I'm going to do is, you may say that, okay, you are biasing this thing. You are basically, why this, if one of them would be movable and the other one is fixed, why one would be in perpendicular direction and the other in the parallel direction? Why don't we repeat the experiment by interchanging these two? Yes, we will do that. So we turn the table by 90 degrees. Okay. And similar calculation we can do. So what would be the result? Let me just show you the little calculation. You can do it by yourself though, but I just thought that I will show you the calculation. So here it is. See the time difference, first time delta t t2 minus t1 is just from the calculation you can find out. It's this thing. Now if we rotate the instrument through 90 degree, M1 becomes M2 and M2 becomes M1. Then L2 becomes L1 and L1 becomes L2. So it's simple. Then the time difference is delta t prime equal to t2 prime minus t1 prime. All right. Now, what I'm going to see is that, is this delta t prime is equal to delta t? If not, I'm not expecting them to be the same because I have rotated, and this rotation should cause a shift in the fringe pattern because it changes the phase relationship between 1 and 2. Okay. Now 1 assumes the role of 2 and 2 assumes the role of 1. The lengths of them have changed. All right. So there is a phase relation between 1 and 2 has changed. So there will be a different time lag in this case. So yes, indeed, delta t prime minus delta delta t, sorry, it will be delta t. If you calculate, this comes out to be this using the binomial expansion and keeping only the terms up to v square by c square, we arrive at this result. This is very simple. Okay. So that's what I have written at the end. So delta t prime minus delta t is this. Now, what is the consequence of that? Are you getting the point that this delta t is not equal to delta t is because of the fact that this rotation has changed the phase relationship between the two waves, and that is why the time lag also changes. Okay.
Sir, I couldn't get why by turning table by 90 degrees results in phase transformation.
The phase relation between these two waves, wouldn't they change if you turn the table, because the path lengths are the different? So earlier, suppose L1 was greater than L2. Now it is L2 is greater than L1. Like that. The arm lengths are different.
Yes, sir.
Sir, then does it mean that if the arm lengths would have been same in the experiment, then the time difference would have been 0?
No, not really that, because apart from that, there is another thing which you are missing. This V factor. This V factor is coming, no?
Yeah, yes, sir.
Right? So it changes
Sir,
the
if
direction
we-
of velocity. Huh?
If we consider it as an YDSC, if path difference is same, then why the phase is changing?
Path difference is same. Who
For
said
example, sir,
that? Path
you said
difference. No. Path difference can change due to two things. You please listen to me carefully. This is the problem, you guys, that you are jumping into conclusions without listening. Different path difference can be same for two reasons. One is the arm lengths can be different. The second reason is that the traveling, the velocity of the light in different direction is different. This fellow V, had this fellow V not been there, then these L1 and L2, had they been same, delta T prime would be equal to T. Again, let me show you the calculation. So here it is, see, L2 plus L1 divided by 1 minus B square by C square minus L2 plus L1. So if L2 and L1 were equal to the same, but V was non-zero, then still there would have been a path difference. On the other hand, if V was 0, then there wouldn't have been no time lag, irrespective of whether L1 is equal to L2 or not equal to L2. So this actually shows that this phase difference is due to the different velocity of light in different directions. Of course, the arm length can be a useful, can be one of the things, but in here, why did we do this 90-degree rotation? This 90-degree rotation completely, suppose you look here. Suppose I didn't rotate it through 90 degrees, okay? Still there is a phase difference. Are you getting my point? Hello?
yes, sir.
Yes,
I'm
sir.
getting.
If V was 0, still you would have 2 by C into L2 minus L1. Okay? So this phase difference or the path difference is coming completely from the difference in the length of the two arms. If L1 equal to L2 in this case, delta T would have been 0. Right? You agree with me?
Yes, sir.
Now, when I did change, rotate it to 90 degree, the idea was the bias that I had in doing the first part of the experiment is being averaged out. So I am now interchanging the role of the two mirrors, just positioning them, one in transverse direction, one in perpendicular direction. Longitudinal direction. That is one in perpendicular direction and one in the horizontal direction. Okay, so that I can completely reduce the bias from my experiment. And as a result of that, if V was 0, what I find out, if V was 0, yes, delta T prime minus delta T would have been 0. Okay. There wouldn't have been any phase change induced time delay. But here we are getting a non-zero delta T prime minus delta T. Then why it is happening? Because it is happening because the velocity of light in two different directions are different. It has been taken to be different. C plus V and C minus V. So because of this V factor, there is a time delay which indicates that the phase difference is due to this two different velocities of light in two different directions. Is it clear now?
Yes, sir.
Okay, fine. Now let's see, what does this mean for us? What does this mean for the experiment that we are carrying out? Now, a phase difference, what does it introduce? Let's see. So if the optical path difference between the beams change by a wavelength, lambda, what would happen? There will be a shift of one fringe, because a change in path of lambda, if I now convert it to time, how much time delay we will have between two wavefronts? It's lambda by C. And the lambda by C difference will shift the fringe by 1, because here it is illustrated, pictorially. So you look at it, that suppose I had this situation. Okay. So these two are perfectly in phase. Now suppose one of them is time delayed or path delayed by a full wavelength. Okay. So here you can see that this originates from here. So there is a full lambda difference between the two wavelengths, the starting point. Okay. So therefore, what I will get the fringe shifted by 1. So if it had started from here, the first illumination would have been here, right here. Instead, the first illumination I am getting here. Do you understand?
Yes, sir.
Yes, sir.
Yes, sir.
So therefore, the fringe would be shifted by the number 1 due to this time delay of lambda by C, which is equivalent to a path difference of lambda. So if a time delay of lambda by C shifts the fringe by 1, what would be the time delay of delta T prime minus delta T shift the fringe into this number? So it's simple. Okay, delta T prime minus T we had calculated, which was this fellow, and then I'm simply multiplying with C by lambda. And so I get this result. So therefore, there should be a fringe shift due to these different velocities of light in different directions, which are due to the fact that there is a ether frame in which light also travels, and the velocity of light is not constant, just like all mechanical waves. So fringe shift is given by this relation. Now, what Michelson and Morley did, so this is analytical calculation, all fine. They obtained an optical path length of L1 plus L2 to be 22 meter, and they put both the arms to be same, so that they can see whatever effect we get is completely due to this movement of Earth through the ether frame, and thus we can detect the ether frame, or we can prove experimentally the existence of ether. So this is the lambda, the wavelength of light used. This is the velocity. And so calculation wise, from this formula, if I simply plug in this number, my delta N should be 0.4. It wouldn't be 1, of course, but you will see some fringe shift. That was the point. But what happened was completely counterintuitive, beyond expectation. Michelson and Morley did not see any fringe shift. There was absolutely no fringe shift. So what they did, they tried several options. They mounted it on a massive stone slab for stability. So they wanted to get rid of all small aberrations that can affect their experiment. They floated the entire instrument in mercury so that it can be smoothly rotated. And in order to make the light path as long as possible, mirrors were arranged on the slab to reflect the beams back and forth through 8 round trips. And fringes were observed under a continuous rotation of apparatus. And the resolution was such that a fringe shift as small as 0.01 of a fringe could have been detected. And they continued the experiment throughout 1 full year, throughout the season change and all that. But no fringe shift was detected. So it was a negative result, but it gave rise to a complete new idea in physics. So what is the interpretation? How could I understand this null result? Is that, see, the apparatus moves with a speed v through the ether. That was our starting premise, that this is actually what is happening. And we wanted to detect this ether frame or prove the existence of this ether frame through this experiment. Now, in predicting the expected fringe shift, we took the v to be Earth's velocity with respect to ether, which is fixed on sun. Now, if v is 0, then delta n is 0. That is from the formula, right? The formula tells us that if v is 0, then delta n is equal to 0. But v cannot be 0 because the Earth is rotating about the sun. It is a known fact. Okay, so experiment, that means the experiment does depend not only upon an absolute velocity of Earth through ether, but also on changing the velocity of Earth with respect to ether. So therefore, we must have seen a non-zero delta n. But experiment could not see a non-zero delta n. That means this this changing motion through the ether would have been easily detectable by precision measurement if there was an ether frame at all. So therefore, we are making a mistake at the very beginning, at the fundamentals, that we thought that there is a eternal ether frame in which the entire universe is floating. So that challenged the concept of ether, and in fact, it effectively ruled it out. And therefore, what Maxwell had found out is that speed of light is same, that is c for all directions in every inertial frame, can now be acceptable. Okay, although it still raised a lot of suspicion, because this means Galilean relativity fails. According to the Galilean relativity, there is absolutely no possibility of anybody moving with a constant velocity through all inertial frames. And then, of course, the ether picture, which was so dear to the scientists, is broken down. Okay, so Michelson Morley experiment was kind of a milestone in the history of physics to give rise to new ideas. Okay, so what was the aftermath? Then, of course, people did not give up easily. They tried to present several possible interpretations of the experiment, and none of them came anywhere close to be foolproof. Each one gave rise to more questions. So if you are interested, you can read up this history. And then finally, the special theory of relativity appeared to answer all questions. How? This is what I'm going to talk about now. Okay. So this is the Michelson Morley experiment, okay, which effectively sealed the fate of this ether idea, ether hypothesis, totally. Okay. So now what happened? How do we resolve these riddles that still constancy of C and the failure of Galilean relativity to incorporate Maxwell's equations for electrodynamics? So Einstein, here came Einstein. Einstein gave this proposition. He told that the difficulty with ether is not a problem of Maxwell's equation, but it is arising from an error in basic dynamical principles, our basic understanding. Go back to the basics. So he said that C is predicted from electromagnetic theory and it involves no reference to a medium. It must be a universal constant, same for all observers. So C is independent of observer's motion. So in effect, what he tried to say is that accept that this is not a mechanical wave, this is an electromagnetic wave, which is characteristically different. So your ideas that has been going on for so many years, that propagation of any wave requires a medium, and then medium changes the velocity of the wave, you throw it out of the window. Here is one wave, the electromagnetic wave, which can travel in any direction without a medium with a constant velocity. And by this proposition, we got a new principle of relativity, which includes not only laws of mechanics, but also all physical laws. Okay. So as this was a very big revelation, very big assertion that Einstein made, that it is contrast to all kinds of mechanical waves. This is a new kind of wave, a different kind of wave, which has a constant velocity across all reference frames in all directions. And in fact, this worked wonders. So with that came the special theory of relativity, with two postulates, which were later on proved to be correct through experiments. So what are the two postulates? First one is nothing really new from the Galilean relativity. The laws of physics are same in all inertial systems. So there is no preferential inertial system exists. In fact, after the Michelson Morley experiment, it was very clear there is no, eternal ether frame, which is godlike. There are tons and tons of inertial frames, which you can choose. All inertial frames are equivalent. The laws of physics do not change from inertial frame to inertial frame. And second is the speed of light in free space has the same value in all inertial frames. In fact, 1 and 2 are related. If 2 is not true, then 1 is not true. And this is very obvious. If the speed of light is different in different inertial frames, then we are back to square one. And then all laws of physics, we already found that using Galilean relativity, the laws of electrodynamics cannot be satisfied. So therefore, if speed of light is not constant, then all laws of physics are not same in all inertial systems. Okay, and this is the Einstein papers. This is just a snapshot of the paper. It's written in German. You can see the publication year. It's 1905. Okay, all right. So fine. These are the postulates, and in fact, this was a completely new idea challenging our intuitions, hitherto all kinds of understanding of the physical world. And of course, there were resistances. Ideologically, people were finding it very difficult to accept it. So Hermann Bondi, in this context, made a very interesting comment, which is worth noting. What he said is that, here I am quoting, the special theory of relativity is a necessary consequence of any assertion that the unity of physics is essential. But it would be intolerable for all inertial systems to be equivalent from a dynamical point of view, yet distinguishable by optical measurements. So someone at the beginning of the class was asking that in the first class, what did it really mean that the optical experiments can be different from inertial frame to inertial frame? What Bondi was pointing out, that is incomprehensible. That from the dynamical point of view, that is from the point of view of their motion, all inertial systems are equivalent. And you are saying that if you make an optical measurement in one frame, the results would be different in another frame. These two are contradictory. So therefore, one has to have a unified structure of physics, a unity of physics, the optical experiments and mechanical experiments and whatever experiments you do, they should not be distinguishable depending upon the frame, reference frame. So special theory of relativity was a necessary consequence of this search for unity in physical world. And then he goes on saying, it now seems that almost incredible that the possibility of such a discrimination was taken for granted in the 19th century. So basically people completely overlooked that there is contradictions in their idea. But at the same time, it was not easy to see what was more important, the universal validity of Newton's principle of relativity or the absolute nature of time. So here he hinted on something that was so far completely neglected in the foundation of the mechanics. That people had put too much emphasis on the Newton's principle of relativity and its validity, its robustness, but they completely ignored the other aspects that goes into it. One of them is certainly time. Okay, so now with this, after this postulate of relativity, this postulate that is ideological, that is philosophical. Einstein up to this point, it was in the idea level because no prevalent ideas were able to solve this riddle. So therefore, postulates of special theory of relativity was the best at that moment. But we have to formulate a program in order to satisfy it. So what was the program of the new theory? What do we need to do? We need to obtain equations of transformations between two uniformly moving inertial systems, which will keep the velocity of light, c, constant. Because that is the second postulate that has to be satisfied. Second is, examine the laws of physics to check whether or not they keep the same form under these transformations. If some of them are not invariant under this transformation, then enforce necessary generalizations. So I am starting from the top and working my way up all the way to bottom. That I know that all physical laws are to be invariant under the transformations between two uniformly moving inertial systems that keep c constant. And so if the structure of the laws of physics, the way they have been written so far, are not invariant under this transformation, then we have to make necessary corrections so that the first point can be, the second point can be satisfied. Okay, up to this point, did you understand that after the failure, one point was failure of Michelson Morley experiment, failure in the sense that the failure of the ether concept, and second is the idea of Einstein, how the ideas did not come, from the blue, out of the blue, but he had been following the thing and he had hit the right point. Okay, took some from the Galilean relativity, the first postulate, and the second one from the Maxwell's equations, Maxwell's laws of electrodynamics. He tried to put these two because his idea was that only this way you can understand, you can have a unified picture of the physical world. Okay, if you do not have any quick question, then let me go ahead. Before proposing the program of the new theory, I will first introduce a new concept. And that is what Hermann Bondi was actually mentioning about the absolute nature of time. And this is what had intrigued Einstein. And he started looking into it very carefully. Any question?
Sir, I have a question.
Huh?
Sir, I have a question.
Yes, go ahead.
Sir, my question is that even in the previous class, we saw that people were very resistant towards accepting the fact that the speed of light c is a universal constant. But when the Michelson and Morley experiment failed, it gave us unexpected results.
Yes.
Einstein said that C calculated from EM wave equation was not calculated with respect to any reference frame. So we came to the conclusion that it is a universal constant. So if we knew this fact beforehand, then why did we conduct so many experiments?
Yes, the reason is because it was challenging our intuition. See, over several hundred years, the subject developed, and people were still thinking in terms of the mechanical waves, right? In case of mechanical waves, like sound waves, the velocity depends on the medium, and velocity changes from medium to medium. This is another wave. So how come it doesn't require a medium to propagate, number one, and then the velocity is constant? So you see, if there is something new, it's kind of difficult to accept. At that moment, the velocity of light was not found. I mean, the constancy of velocity of light was not proved experimentally. Okay, let me tell you that. But Maxwell's, the laws, they were tested. They were tested, and this constancy of C was an important piece in writing down those equations. So since these laws, what these laws proposed, they were tested by experiment. So these laws have to be correct. Now the form of the laws have this C, the velocity of light, into it, and it's a constant. Okay. So people were feeling that, yes, Maxwell's laws of electrodynamics are also correct. And but they were still unable to comprehend that there can be a wave who doesn't need any medium for propagation and whose velocity is constant from inertial frame to inertial frame. Because that was challenging the Newtonian relativity. That was the thing. Okay.
Thank you, sir.
All right. So let's, little time we have, let me move ahead. So now, as I said, that the time was the culprit. That was the suspicion of Einstein. So here we are going to introduce a new concept that is called, or not really new concept, but examine the concept of simultaneity. Remember that in the first lecture, among the first few slides, I had shown you a picture of a fish swimming in the water. And I said that if you want to measure the length of the fish, what do? You measure the tail end of the fish and the front end of the fish at the same time, simultaneously. Okay. And then just take the measurements in space and get the difference. That is the length of the fish. So this simultaneous measurement is an important concept. And in fact, in Newtonian mechanics, you see the time really never came up for discussion. Same time scale applies to all inertial frames. So it was implicit that there is a universal time scale in the framework of Newtonian relativity. Okay. Now, what is this universal time scale? What do I mean by that? How do you set it up? How do you conceptualize this universal time scale, or do the measurement using a universal time scale? So universal time scale means we have a time scale which is independent of reference frame. Okay. Now fine, but then we have to give a proper meaning to statements like events A and B occurred at same time. We keep on saying, right, these two events occurred at same time. So Einstein, for example, pointed out that when we say that a train has arrived at 7 a.m., this means we are talking about two events. One event is I have a clock which is pointing at 7, and there is another event, that is the train arrives. Simultaneously, these two events are happening. Okay. But the point is that then based upon that, if we can set that as the reference, then we can sort of give a statement on simultaneity of event. But the question is, can we set up a universal time scale across all the reference frame, all the inertial frames? Okay. For example, here, what you see in the slide, there is a quiz competition and there are two participants, Alex and Bob. So they have to press the buzzer. It's a rapid fire round. They have to press the buzzer. Whosoever presses the buzzer first will be the winner. Now the quiz master has to find the first one to hit the buzzer. Now, from the conventional experience, we know that if Alex and Bob were nearby at the same location, we could record the times at which each one of them had hit the buzzer and decide the order, who has hit the buzzer first. But suppose they were in very different locations. Suppose Alex is sitting in Guwahati and Bob is sitting in Kashmir. Okay. Then, can I use a single clock to decide the order? That would be wrong. Because how do you know that 7 a.m. at Guwahati is also 7 a.m. at Kashmir? How do you decide? Okay. We can only say that yes, 7 a.m. at Guwahati is 7 a.m. at Kashmir if our clocks are synchronized. So synchronization of clock, if that is possible, then we can chronologically order the events, that is, which has occurred first. Now, how do we synchronize clocks? What do we mean by synchronization? It means that the simultaneous setting up of the clock based upon simultaneous arrival of some signal. Okay? So, what is the best way of synchronizing clocks? There are several ways, but the best one, or one of the best, is like this. So first you place two clocks in two locations, A and B. Instead of Alex and Bob, let's call them A and B. Now, say from Guwahati to Kashmir, find the midpoint, O, along this distance. Now flash a light signal. When A and B receive the light, they set their clocks to predefined time, say 00, their time starts. This is based on the fact that light has same speed in both directions. So if I am flashing a light at the midpoint in the straight line connecting Guwahati and Srinagar, and then flash a light right at the midpoint, the light flash will reach Guwahati and reach Srinagar exactly at the same time, because the lengths are same. And then the person sitting in Guwahati and the person sitting in Srinagar, they can set their clocks to a predefined time. Then only we say that the clocks are synchronized. Okay? Do you get my point?
Yes, sir.
Yes,
Yes, sir.
Information of clock is very important before giving a statement that these two events are simultaneous.
So can you repeat it again?
Huh?
Can you repeat it again?
Have you ever experienced this thing that in the television, maybe this happens for a few seconds, in television, a program starts in your place, or maybe, you know, it's a fast-paced thing. Suppose you are watching a cricket match, okay, and there was a wicket down. Your friend reacts little late. Your friend who is far away reacts a little late, because in his TV set the signal that has arrived has a little bit of delay. So they receive this signal of that event, of this wicket falling a few seconds later than you. Have you ever heard of such things? Or you haven't noticed such a thing?
Yes, sir.
Yes, sir.
Yes, sir.
Why is that? Why is that? The clocks appear to be synchronized, but that happens. So this is
Sir,
a
once
case
it has
of,
happened to me.
So therefore you cannot say that everywhere in India this event is happening simultaneously. Our clocks are not synchronized. Our clocks are not synchronized because we haven't synchronized them, and we haven't synchronized them, we couldn't synchronize them because the signal reaches different places at different times with slight delays. Okay. All right. So this is about the synchronizing the clocks. That is making them in a single reference frame, all of them to set to a predefined time without any bias. Okay. Now, Fine, I have synchronized clocks, but still there is a problem. Suppose I have an observer in an inertial frame S finds two events A and B to be simultaneous because he has synchronized clocks in the location of event A and event B and record identical time. Will these events be simultaneous by an observer in an inertial frame that is moving with speed v with respect to first? So I have two inertial frames. One frame is moving with a velocity v with respect to the other. I mean, the observer in each of the inertial frame has synchronized his clocks. So he is recording two events to be simultaneous. But does that mean the other observer would also record them to be simultaneous? Let's examine that with a simple, very simple kind of experiment. So here is the situation you see in this picture. There are rods, meter scales. Okay. So I have S frame and S prime frame. They have their own meter scales, meter sticks, and synchronized clocks. Each one of them have synchronized their clocks in their own frame. Now, what are the events that we are going to record? Is that two lightning bolts strike each end of this thing, end of these rods at these points, A and B in S frame and A prime and B prime in S prime frame. Okay, and leaves permanent marks. Now, assume that afterwards by measurement, each inertial observer finds that he was located exactly at the midpoint of the marks, which were left on his reference frame. So that means each observers know they are at midpoint. He will conclude that the events are simultaneous because you see lightning had hit these 2 points. And if the signal from these two lightning reaches the observer at the same time, he will say that this is simultaneous because at the location A and at the location B, he has kept two clocks which are synchronized. Both are set at time 0. And then the lightning hits, the signal travels, and he finds that the signal travels to him at the identical time. I mean, the time that is being clocked by A and B. So he calls it simultaneous events. Okay. Now question is, suppose I take the viewpoint of observer at S. So he says, yes, the A and B are produced simultaneously. Events A and B are produced simultaneously. But is it simultaneous for observer at S prime? Let's see. Now at the instant, the lightning strikes A prime, these 2 points coincide. And at the instant lightning strikes B prime, they also coincide. And this is where we start our observation. So S observer finds these two events to be simultaneous. So the midpoint O and O prime in the two reference frames, they also coincides. Now, look at the second picture. This is the first picture. This is when we start the measurement or start the observation. Now, the light signal reaches this observer at O from B and from A. Now, by the time the light signal reaches the observer at O from A and B, this rod, this S prime frame has moved to the right. So the O prime point, which was at that instant was coinciding with O, has actually moved to the right. Okay. So the signal from B will reach the point O prime first, then the signal from A reaching the O prime point. So the signal from, or rather I would say signal from BB prime arrives at O prime before it gets to O. And during this time, the O prime has traveled to the right. So signal from BB prime arrives at O prime before it gets to O, whereas signal from AA prime arrives at O before it gets to O prime. Therefore, For the S prime observer, the event BB prime has happened before AA prime because the signal from AA prime takes longer to reach OO prime as compared to the signal from BB prime. Okay, so what was simultaneous in S frame is not simultaneous in S prime frame. The same thing or the opposite thing happens if I take the point of view from S prime observer. So that for now over here, the S prime observer considers these two events to be simultaneous. Now, when these two are simultaneous in S prime frame, are they simultaneous in S frame according to the observer? Now you see here. Over here, with respect to S prime, S is moving to the left. So now, when the lightning has struck and S prime considers them to be simultaneous, when the light from BB prime will reach, the light from BB prime would be taking a longer time to reach the point O. Before that, the light from A prime will reach O. So you see here the distance is shorter than this distance. So as a result of that, for the observer at S, the event AA prime will be happening before the event BB prime. It's exact opposite to what was inferred in case of the observer in S prime. So therefore, what is simultaneous in one inertial frame is not simultaneous in another inertial frame, although in each of the inertial frame, their own clocks are synchronized. So what does that mean? What is the interpretation or conclusions from this little experiment? Is that the simultaneity is a relative concept, not an absolute one. So the time interval of events as measured in one frame is different as measured in another frame, moving with a constant velocity relative to the first. And this affects the length measurements also, because now imagine that length of the fish. I said that the tail end and the front end, their positions are to be measured simultaneously. Now, of course, when I'm talking about simultaneously, I'm talking about giving the statement with respect to one reference frame. That could be the reference frame on Earth, on the ground. Now, what is simultaneous in the ground's reference frame is not simultaneous in the reference frame in which the fish is moving. That is the fish's own reference frame. So those two events are not simultaneous. So therefore, the length of the fish cannot be measured that way because these two events would not appear simultaneous for an observer who is sitting with the fish. So therefore, the time interval of events, the length measurement, all will be affected because of simultaneity being a relative concept. And we will see that what is the consequence of that, how it leads to more kind of confusing, or I would rather say counterintuitive ideas leading to the sort of hallmarks of special theory of relativity. Okay. So I end the lecture here. So tomorrow we will formulate, we will write down the transformation equations, and then we will see that what are the consequences it leads to in terms of the frame dependence of time interval of events and length measurement.